Welcome back to Chapter 3 of Principles of Mathematical Analysis. So far, we have studied convergent sequences, subsequences, and Cauchy sequences. In this section, we broaden our vocabulary to handle sequences that may fail to converge. We first define what it means for a sequence to diverge to plus or minus infinity. And then we introduce two robust quantities, the upper and lower limits, which always exist in the extended real line. They will let us speak meaningfully about the asymptotic ceiling and floor of any real sequence, convergent or not. Here's the plan. After motivation, we give definition 3.15, which formalizes divergence to plus and minus infinity. Then definition 3.16 introduces the set of subsequential limits in the extended reals, and from it the upper limit S star and the lower limit S sub star. Theorem 3.17 records the two key properties that characterize the upper limit, and we work through its proof in cases. Examples 3.18 give us a feel for the new objects, including the important fact that the ordinary limit exists exactly when the upper and lower limits agree. We close with the comparison theorem 3.19. Many real sequences we meet in practice simply fail to converge. They may oscillate, like the sequence whose values alternate between +1 and -1. Or they may grow without bound. The plain notion of limit then has nothing to say about them, and we lose a useful summary of their long-run behavior. Even when the limit does not exist, a sequence often has a clear upper and lower envelope in the long run. Think of a wave whose amplitude settles down to a fixed range. The terms keep dancing inside that range without picking out a single limit value. But the range itself is unambiguous, and we want a way to talk about it. The subsequences of a sequence often do converge, even when the sequence as a whole does not, and their limits give us a finer record of what is going on. Recall from Section 2 that a number is a subsequential limit if some subsequence converges to it. We collect all such values, together with possibly plus and minus infinity, into a single set, and we will define our two new quantities as the supremum and infimum of that set. The payoff is that the upper limit and the lower limit always exist in the extended real number system, no matter how badly behaved the sequence is. They give us a uniform language for asymptotic behavior, and they reduce to the ordinary limit exactly when the sequence does converge. Let us begin with the divergent case, where we extend the arrow notation. The definition formalizes what it means for a sequence to grow without bound. The first version says, no matter how high a target value m we pick, the sequence eventually stays at or above m for the rest of time. The second version is symmetric. No matter how low a target m we pick, the sequence eventually stays at or below it. The role of m is the same as the role of epsilon in ordinary convergence. It lets us quantify how far out we have to go. Here is the picture for divergence to plus infinity. The horizontal axis is the index n, and the vertical axis is the value s sub n. The dashed orange horizontal line at height, m, is the threshold we are testing against, and the dashed vertical line at n marks the cutoff. The blue dots show early terms scattered below the threshold. The red dots past index n all lie at or above m. The point of the definition is that we can repeat this picture for any target m by choosing n large enough. A small but important warning about notation. We are now writing arrow plus infinity for sequences that diverge in this strong sense, even though, strictly speaking, they do not converge to anything in the ordinary metric space sense. The arrow is the same symbol we used in definition 3.1, but it is being applied to a different situation. The original definition of convergence and of limit is in no way changed. This is purely a notational extension to cover divergence to plus or minus infinity. The starting point is to collect all the asymptotic values the sequence can produce. Look at every subsequence and record what it converges to. The values live in the extended real line, so plus infinity and minus infinity are allowed if some subsequence diverges to them. The set E is the catalog of all these values. It contains the ordinary subsequential limits we introduced in definition 3.5, and possibly the two infinities as well. Now we extract two single numbers from the set E. The supremum of E, taken in the extended real line, is the upper limit S star. The infimum of E is the lower limit S sub star. Because supremum and infimum are taken in the extended line, they always exist. The worst that can happen is that they are plus or minus infinity. So upper and lower limits are universal. Every real sequence has them. Two pieces of standard notation. The upper limit is written lim sup of S sub n as n goes to infinity, and the lower limit is written lim inf. You will also hear them called the limit superior and limit inferior. The names are well chosen. Each is a kind of limit in a generalized sense that always exists, even when the ordinary limit does not. Whenever the ordinary limit does exist, both will collapse onto it, as we will see in a moment. We will use these symbols frequently from here on, especially in the convergence tests for series later in this chapter, where the ordinary limit is often unavailable, but the lim sup is always at hand. With the notation in place, let us draw a picture. Here is the geometric picture. The horizontal axis is the extended real line. The four blue dots mark the subsequential limits of some imaginary sequence, -2, 0, 1, and 2. The orange brace below shows the entire set E of these values. The upper limit is the largest, sitting at 2, and the lower limit is the smallest, sitting at -2. In general, the set E can be much bigger than 4 points. It can be a whole interval, or even the entire extended line. But the upper and lower limits are always its supremum and infimum. Before going further, an important observation. The set E is never empty. Some asymptotic value always exists, so the upper and lower limits are always well defined. The argument splits into three cases. First, if the sequence is not bounded above, we can pick out terms growing arbitrarily large, giving a subsequence diverging to plus infinity. So plus infinity belongs to E. Second, by symmetry, if the sequence is not bounded below, some subsequence diverges to minus infinity, so minus infinity belongs to E. Third, if the sequence is bounded in the reals, then all its terms lie in some closed bounded, hence compact, interval. By theorem 3.6, the Bolzano-Weierstrass theorem from section 2, some subsequence converges to a point P in that interval, and P belongs to E. In every case, E contains at least one point, so it is non-empty. Theorem 3.17 pins down the upper limit by listing two properties that determine it uniquely. The first property says that S star is itself a subsequential limit. That is, S star belongs to the set E. The supremum of E is achieved as one of its members. This is not automatic for general sets. It relies on the specific structure of E. The second property says that nothing strictly above S star can be reached infinitely often. Pick any threshold x larger than S star. Then the sequence eventually stays below x. So while S star is achieved as a subsequential limit, nothing above it is. This is the upper bound aspect of the supremum, expressed in sequence language. Together, properties A and B pin down a single number. The theorem asserts that S star is the only candidate satisfying both. So we have an alternative description of the upper limit, sometimes more useful in proofs. It is the unique value that is itself a subsequential limit, and above which the sequence eventually does not return. The same statement, with inequalities reversed, characterizes the lower limit, ses sub star. Here's the picture in cartoon form. The horizontal axis is the real line. The orange brace below spans the entire set E of subsequential limits. The smaller blue dots are some of the values in E, and the larger red dot at the right end of the brace is S star, the largest value in E. Property A is the statement that the red dot belongs to E. That is, some subsequence actually converges to S star. Property B looks to the right of S star. Pick any threshold x strictly above the red dot, drawn as the dashed orange vertical line, and the sequence eventually stays to the left of it, with no return trips, so nothing from E can sit to the right of S star. Both properties are visible in this single picture. Before diving in, here is the high-level strategy. For property A, we split into three cases according to whether the upper limit is plus infinity, a real number, or minus infinity, and we handle each separately. For property B, we argue by contradiction. Assuming the conclusion fails, produces a subsequential limit above S star, which is impossible. Uniqueness follows from one short observation. Let us go through each case in turn. Start with the case that S star equals plus infinity. By definition, this means E has no real upper bound. So E is unbounded above as a set. If E were unbounded above, but the sequence S sub n were bounded above, every subsequence would also be bounded, and no subsequential limit could exceed that bound. So the sequence itself must be unbounded above. From an unbounded sequence, we can pick out terms growing without bound, giving a subsequence diverging to plus infinity. That subsequential limit is plus infinity, which is exactly C star. Next, the case where S star is a finite real number, then E is bounded above. Theorem 3.7 from section 2 told us that the set of subsequential limits is closed. Combined with boundedness, the set is closed and bounded. Theorem 2.28 from chapter 2 says that the supremum of a closed bounded set of real numbers actually belongs to the set. Putting the two together, S star is an E. The last case is S star equals minus infinity. The supremum of E is minus infinity only if E itself contains nothing above minus infinity, which means E is just the singleton minus infinity. In particular, plus infinity is not in E, so the sequence is bounded above, and no real number is a subsequential limit. Now suppose, for some real m, that S sub n exceeds m for infinitely many indices. The corresponding subsequence is bounded above by the bound on the original sequence and below by m. So Bolzano-Weierstrass produces a real subsequential limit at least m. That contradicts our finding that no real subsequential limit exists. So past some index every term lies at or below m, which is exactly divergence to minus infinity. The single element of E is then minus infinity, equal to S star, and we are done with part A. Now property B, argue by contradiction. Suppose the conclusion fails, there is some x greater than S star, and yet E's sub n is at least x for infinitely many indices. Pull out a subsequence consisting of those indices. Every term is at least x. Now consider two cases. If this subsequence is bounded above, Bolzano-Weierstrass gives a subsequence converging to a real y at least x. If it is unbounded above, a subsequence diverges to plus infinity, which we treat as y equals plus infinity, again at least x. In either case, y is a subsequential limit of the original sequence, so y belongs to E, but y is at least x, which is strictly greater than the supremum of E. That is impossible, so the contradiction proves B. For uniqueness, suppose two numbers p and q both satisfy properties a and b, and assume without loss of generality that p is less than q. Pick any x strictly between them. Since p satisfies b, the sequence is eventually below x, but q satisfies a, which means some subsequence converges to q, and q is strictly above x. A sequence that is eventually below x cannot have a subsequential limit above x. So the two are incompatible, and we conclude that there is at most one number with both properties. Combined with the existence proof, that unique number is S star. The first example is the most extreme. Take any sequence whose terms run through all the rational numbers in some order. Such a sequence exists because the rationals are countable. Now any real number, x, rational or irrational, is the limit of some sequence of rationals. So we can extract a subsequence of our sequence converging to x. In other words, every real number is a subsequential limit. Plus and minus infinity are also subsequential limits, since the rationals contain arbitrarily large positive and negative values. So E is the entire extended real line, and its supremum and infimum are plus and minus infinity. The second example is the running prototype. The sequence alternates sign by way of -1 to the n power, and multiplies by a factor that approaches 1 as n grows. The even index terms are positive and converge to +1. The odd index terms are negative and converge to -1. So +1 and -1 are the two subsequential limits, and they are also the supremum and infimum of E. The upper limit is 1, and the lower limit is -1. Even though the sequence itself does not converge. The picture shows the two subsequences side by side. The horizontal axis is the index n, and the vertical axis is the value s sub n. The upper dashed red line at height +1 and the lower dashed red line at height -1 are the two asymptotic levels. The blue dots are the even index terms, creeping up toward +1 from below. The orange dots are the odd indexed terms, creeping down toward -1 from above. The original sequence interlaces these two strands and never settles, but each strand converges. The upper level is the limit superior, and the lower level is the limit inferior. The third example is the most useful general fact. A real sequence converges to S if and only if both its upper and lower limits equal S. The forward direction is straightforward. If the sequence converges to S, every subsequence also converges to S, so E is just the single point. S, and its supremum and infimum both equal. For the converse, suppose lim_sup equals lim_inf equals S, then E is just S alone. If the original sequence did not converge to ES, we could pull out a subsequence whose terms all stay away from S by some fixed positive distance. By compactness of the extended real line, that subsequence would have a sub-subsequence converging to some point, and that point would be a subsequential limit of the original sequence, different from S, contradicting E being just one point, so the sequence must converge to S. The practical takeaway: lim_sup and lim_inv together carry all the asymptotic information about the sequence. Convergence is nothing more than the two of them agreeing. Here is a simple but very useful theorem. If one sequence stays at or below another from some index onward, then the upper limit of the smaller sequence is at most the upper limit of the larger, and likewise for the lower limits. The order between the sequences carries over to their asymptotic ceilings and floors. The book labels the proof trivial. The intuition, any threshold x greater than the upper limit of t sub n, is eventually exceeded by neither sequence, because t sub n stays below x, by theorem 3.17 part b applied to t, and s sub n is at most t sub n. So x is also a threshold for s, which forces the upper limit of s to be at most the upper limit of t. On the next slide, we make this argument rigorous for the upper limit. The lower limit case follows by symmetry. Let us walk through the proof of the upper limit inequality. Write S star for the upper limit of s sub n and t star for the upper limit of t sub n. Our goal is s star at most t star. If t star equals plus infinity, the inequality is automatic. Otherwise, fix any real x strictly greater than w star. Theorem 3.17 part b, applied to the sequence t sub n, gives an index n sub 1 passed, which every t sub n is less than x. Combine this with the hypothesis s sub n at most t sub n, which holds past index n, and we get s sub n less than x for every n past the larger of n, and n sub 1. So the tail of s sub n stays below ex. That forces every subsequential limit of s sub n to be at most x, so the supremum of those limits, which is s star, is also at most x. Since x was any real number strictly above t star, we conclude s star is at most t star. The lower limit inequality follows by a symmetric argument, or by applying what we just proved to the negated sequences. Let us recap. We started by formalizing what it means for a real sequence to diverge to plus or minus infinity. The arrow notation now applies in this extended sense, while ordinary convergence is unchanged. We then collected all the subsequential limits in the extended real line into a single set E, and defined the upper limit as the supremum of E and the lower limit as the infimum. Crucially, these always exist for any real sequence, even one with no ordinary limit. Theorem 317 characterized the upper limit by two properties. It is itself a subsequential limit, and the sequence eventually stays below any value larger than it. These two properties pin down S star uniquely. The lower limit is characterized symmetrically. The most practical takeaway is the convergence criterion from example 3.18 part C. The ordinary limit exists if and only if the upper and lower limits agree. We also recorded the comparison theorem 3.19, which says that order between two sequences is preserved by their upper and lower limits. Coming up next is a short interlude on some special sequences. We work out the limits of a few concrete expressions. N to the power p to the Cauchy n, and the t root of n, among others. These are workhorse facts that we will reuse throughout the rest of the book, especially in the root and ratio tests for series later in this chapter, where the upper and lower limits we just introduced will play a starring role. See you in the next section.